Good morning, everyone. So this year there will be less, we can say, activity on the compositional side, but still you will have some information, compositional information in the two exercitation, one for the Moon and one for the Mars. So here will be an introduction to what is generally composition information, in particular the reflectance spectroscopy. And following me, Beatrice and Francesca will give you some more issue about, or more information about the respective exercitation, Mars and Moon. So generally, what we are going to explore as information of the composition are acquired in particular in imaging system that are not so many different from the typical image that you can have from a camera, but just you have a multiple or several number of wavelengths that has been acquired together to compose a image with several wavelengths that have to have different information, not only from a morphological point of view, but also the information related to the composition. Technically, you can have two different, in particular, range where I have information about the surface of another planet from remote sensing. And this is for related to elementary information, so the information about different elements that are present on the surface. And this is mainly done in X-ray and gamma ray. Then the higher number of information that we have that is much more related to mineralogy is acquired in the considering the spectral information from the visible to the near infrared. In this spectral range, we can study it thanks to the spectroscopy. So thanks to the interaction between an energy and the surface, different type of absorption process that are related to typical electronic transition or molecular transition. The previous are generally related to the presence of some transitional metal within the material present on the surface. And so give us information about, for instance, mafic mineralogy. And the second is much more related to the vibration of the crystal lattice. And so it's much more related to the presence of hydrated minerals or carbonates, and they are generally expressed at slightly longer wavelength than the electronic one. Just to see a little bit more what generally happens when, in particular for reflectance and emittance, when the light hits the surface, we know that generally the light is scattered, and we can acquire a portion of this information as reflected light. But the same way, the light can be absorbed or transmitted depending from the properties of the material. And moreover, in some cases, it can be emitted. In some cases, it can be emitted just because the material is radioactive, so it's emitting by itself, but often is emitted because it absorbs some light, and after this light has been absorbed, can be emitted by the surface. All of this process permit us to have a spectral variation. So in the different spectral range, we can have a variation of the reflectance and or of the emittance that give us, we can say, a fingerprint of specific material. Here you can clearly see, for instance, then when the light hit a grain of olivine, will give us spectral information. If I'm not sure if you're going to see my mouse, but in the right plot on the top, you can clearly see as the reflectance is changing the wavelength. So there is a correlation between the energy and the light that is reflected. And in some area, this light is less reflected than another. This less reflection that is due to some specific absorptions permit us to have this kind of fingerprint, so to have a specific and diagnostic information that can be translated in definition of a specific absorption and then of specific minerals that is present on the surface. So, okay. The same things is for the emittance. So in this case, we are going to see the light, the information, the radiation that is emitted, but the process is more or less the same. We'll have some region that is more emitted than other within the different wave. wave number or wavelength that we are looking, and where this energy is less emitted or more emitted, permit us to have some specific information that is correlatable with specific mineralogy. In this case, it's much more due to the vibrational process, and so the asymmetric or symmetric stretches that are present in the crystal lattice. You already see yesterday from Ricardo that generally we call this dataset a 3D dataset, since we are exploring when it's an imaging spectral acquisition, the surface. So in the XY, we have the pixels that characterize the surface. In the third dimension, we have the composition of all of the wavelength that we are acquiring. If it's a multispectral sensor, generally it's due to different filters that are present in our sensor. Whereas when it's an hyperspectral dataset, generally we have a grating in general that is highlighting, is dispersing the light, and so permit to have this kind of information with a higher detail. The acquisition is generally made with following two different modes, and those are just technically related to how the instrument is built. We are not going to enter much more in this detail, but since in general we have a mode that is called push broom, and it's just like a line that is acquired during the movement, so along the track of the spacecraft. And so then we are going to combine a certain number of this line to have the surface information, whereas all the we can say y information that is acquired for each line of samples are related to the different colors or the different wavelengths. The other mode that is called whisk broom is generally working acquiring the information pixel by pixel across the track, so moving or scanning from right to left with respect to the scan. So mainly the information that we have from different surfaces is related to the information to the reflectance in the visible to near infrared. This is mainly done for two specific effects. One is that it's closer to the wavelength where we generally have an imaging system like a camera. So it's closer to be translated from a camera to an hyperspectrometer. And the other way is that because more or less all the surfaces can reflect enough light to have enough information to be acquired by an instrument. As already anticipated before, but here just put a little bit more in clear view, we can have in this spectral range two different types of transition. The electronic one that generally is dominated by those that we call crystal field are for giving information from the visible to circa 2000 nanometers, so 2000 nanometers. Whereas the vibrational one that is called overtone in this spectral range, because it's a propagation of the principal tone that has a longer wavelength, more or less are present from 1000 to longer nanometer, so the longer wavelength. The previous one is generally related to electronic transition, so the presence of some elements that can some transitional elements like iron that can have different electronic jump in a crystal lattice, whereas the vibrational one are related in general to stretching due to the OH in silicate or sulfate or to the carbonates ions. Cations. The reflectance spectra is then controlled also by several other factors. So not only the mineralogical information is present or the single mineralogical composition is present, but the presence of more minerals in the same pixel or the dimension of the grains of the crystals, as well the type of surface can control the range of the spectral level. What is important anyway to remember is that the absorption are then characterized by only the composition. This can be done by a single mineral where only one mineral is absorbing the same wavelength range, or by more than one mineral if more absorption process can be present in the same small spectral range. From those absorptions that are in some way our fingerprint to understand which mineral phase is present, we are generally considered three different important parameters. The position of the band that is related with the energy and so with the selected site of coordination and is translated with the presence of a specific mineral. The intensity of that is generally correlated not only with a specific mineral but with the mixing of more than one phases, and so can give an information also of the presence of that minerals mixed with other. Or the bandwidth that is much more related to vibronic processes, so to the presence of different temperature of the surface or different pressure on the surfaces. Here you can clearly see just a summary of some of the mainly mineral phases that we can recognize in the process. So clearly you see on the left side some electronic absorption that are wider and often stronger than the molecular one that we can recognize in the visible to near infrared. And they are generally characterized in minerals like pyroxene, olivine, or even some ferric oxide, as well plagioclase, mainly due to the presence of iron in specific coordination site. On the right side, you see some of the example for some hydrated silicates and hydrated sulfates. You can clearly see as these absorption are generally narrower, more V-shaped, we can say, and often asymmetric. This is due to the presence of the combination of more overtone in the same wavelength range. This kind of information can be then studied generally following two different approaches when we are looking to some images from remote sensing, or try to specifically classify an image with some kind of tools, or study specific spectral parameters that permit to summarize the information that we have in a lower number of wavelengths. So the previous one is generally more stronger when you are able to classify the surfaces, giving a fingerprint for each unit that you can separate that permit to reclassify all the unit and combine in just one spectrum that summarize the information or the important absorption that you have in that area. But it's more complicated and is more and is taking into account that some end member has to be selected before. So in some ways, not like to be applied for all the image or all the area or all the planets, but you have to consider some knowledge about the specific region that you are investigating. Whereas the spectral parameters can be retrieved for all the images that you want. In some cases, you will have an information that is closer to zero anyway, giving you information that that phase or that type of information that you are extracting are not present. Since you are reducing the high number of wavelengths you have in just few wavelengths, permit to be even less weight in the calculation, so easier to perform in a higher number of images in a few times. And permit also to have a comparison of that kind of parameter in different areas, because you don't need to have any end members to be selected from that specific area. Just eventually you will have the information that there is no information from that specific parameter. Here we'll go to some small cases, and then I will leave the talk to the other colleagues. So for instance, this is a specific case where a tool like spectral angular mapper has been applied to a region of Mars to separate from a compositional point of view the information of different lava flows. We are in the Daleplano, southern to the Tarsis region, and here has been used the near spectral properties from each lavas that were before characterized by a morphological point of view. Assigning that information has been classified the region, and some specific lava flow could be separated in a higher detail thanks to the composition information. So specific morphological units has been then subdivided into more composition units, whereas some of them was perfectly correlating composition and morphology. From the classification, we could retrieve for each unit specific spectral properties that then could be analyzed to have the different information about, in this case, is pyroxene or olivine present on those lavas and how the composition of those lavas was changing. Here in another case, using and considering instead the data from Mars, but where in particular hydrated minerals are present. And you can clearly see that the hyperspectral data, so the spectra with the field by several wavelengths, can be summarized considering just few wavelengths. In this case, it's for instance 3 wavelengths, to calculate the band depth of the absorption. So the summarizing thanks to just 3 wavelength extremes, so the position of the band and the 2 shoulder, the spectral information, and from that calculate parameters that can be then highlighted thanks to some density slice approach or some threshold approach to visualize on the surface those information. And here, for instance, you can see from the right images some of the region where the band at 1.9 or 2.1 micron was a rise, or a band at 2.4 micron was a rise, or some specific parameters related to some minerals like calcium pyroxene or some ferroxide that was so visualized. Once you put this information in the up to your morphological images, and then you take some cutting of the surface, you can clearly put the composition information of the different minerals on that, and so reconstruct the geology, and so combine the composition to the typical mapping, and so separate not only the different highlight the different stratigraphy, but also add the composition information on that. So following me, you will see something related to the moon that is going to the direction of the visitation of tomorrow. So some data set related to the moon will be introduced, and so you will have some indication for the area where you are going to take the exercitation about which data you will have, and so which kind of information then you could add to the map that you're going to draw. And the same case you will see from Mars, where you will have much more details related also to the hydrated mineralogy that is present in the area that you're going to map on Thursday. And in particular, the introduction with the CRISM dataset that has a hyperspectral high spatial resolution information about Mars.
So we are going now to talk about some application of what you see before from Cristian, and in particular, I will introduce you some of the high-level products from the moon. Okay, there are several missions that acquire data from the moon, and in particular, I show here you the mission that acquire data from cameras and spectrometer, so multi-filter cameras and spectrometer. We have the famous Clementine mission, which acquired data in 1994. Then we have Kaguya from JAXA, and the Chandrayaan-1 mission, which is an Indian mission, which explored the moon with an imaging spectrometer, and then also again the Lunar Reconnaissance Orbiter from the NASA, which has the a multi-filter camera. Let's start with Clementine, which is one of the main instruments you will analyze the products. Clementine was equipped with a ultraviolet and visible camera, which has 6 filters and cover a range of wavelength between about 400 and 1000 nanometer, which is the typical range of operation of a camera. And the pixel resolution during the acquisition in each single orbit was among 103, about 300 meters per pixel. You see here the typical RGB map from Clementine mission. And in this map, you see that you have three different ratios from in the three channels. So you have the red channel with the ratio between the wavelength, the band at 715 nanometer and those at 415 nanometer. Then we have in blue, in green, I'm sorry, there is a mistake here. You have the blue and the green is inverted. So in the green channel, you have 700 and 1000 nanometer, and in blue 415 and 750 nanometer. Why these ratios are important? Are important because each one give information on what we can see on the composition of the moon. So also with a multi-filter camera with few channels, we can extract a lot of information. The red channel indicate region with low titanium and high glasses content, while green channel is more sensitive to the iron amount, and so it can be used to map the mafic minerals. Then the blue channel is more typical of high titanium regions. But why we choose these ratios? And how we choose the spectral ratio? First of all, we need to have an idea of what is the mineralogy of the body we are studying, and also consider the analogs of these bodies. In the case of the moon, I show on the left a plot where you see some analogs from the moon sampled for the Clementine filters. So it's like you see a spectrum of these analogs, but as you could see from Clementine. And you see that each one of these has different spectral characteristics in different regions of the spectrum between 400 and 1000 nanometer. So looking the characteristics of the slope, of the spectral slope of the spectrum, you see, you can characterize also and define the spectral ratio that can be useful to map this kind of phases. In the center, I just show you an example of the spectra from the moon of three typical soils of the moon. So the highland, which are mainly featureless and spectrally redder than the other, the Mare crater, which show the typical band of pyroxenes at 1 and about around 2 micron, and then you have the typical spectrum of the Mare soil, which appear more flat and darker than the other. When we say spectrally redder, we say that reflectance increase with the increasing wavelength. While when we say spectrally bluer, we say the opposite, so that reflectance decrease with increasing wavelength. So you will hear this definition often in the next day or when you speak about the spectral data. Then another useful way to select the iteration to see what can be the characteristics of different regions is to use scatter plots. And in this case, you see the ratio between 415 nanometer and 750 nanometer versus the reflectance for some of the Apollo landing site regions. And these are from Clementine, and also in this case you can see the different trend among different terrains, and it is another way to discriminate the spectral characteristics of different regions on the moon, but also on other bodies. And you see also another plot similar that distinguish the Maria from the islands in the bottom plot. And then using this kind of methods, they define the ratios that are useful to discriminate different terrains on the moon. So we see in the map that the island appear redder than the other regions, and this is because they have glasses agglutinate that are due to the bombardment or micrometeorites, and this is a typical indicator of the maturation of the terrain. But also pyroclastic deposit can be red also because of the presence of the glass content. Then we have yellow regions, and in this case we have that the concentration of mafic minerals dominates, but this is not pure, and because you have also a content of glasses, so in some way you see a combination of these two kinds of effect, and you see this typically in the region, in the Mare, in the region I selected here, which is the Aiken basin. Then when we go to the blue unit, so when the blue unit dominates, we are in presence of a high titanium regions, and these are shown mainly in some localized area, which is close to the Tranquillitatis Mare Tranquillitatis, and in this other area in blue, you also have other region but more localized than this. Then also with Clementine camera, multi-filter camera, you can obtain the iron and titanium map. So you can see how many information you can have from a multi-filter camera. To do this, some authors use a more complicated way to define this kind of map, and they use both the Apollo samples from the moon and they use the data from the Apollo samples from Clementine. They used a scatter plot which can be indicative of the presence of iron and terrain maturity. You see on the left, so you have the ratio between 950 and 750 nanometer and versus the reflectance, and they calculated the angle of each group of samples. And here then this angle is indicative of the presence of iron. Then they compare the abundance they found in the samples from the Apollo mission and the angle they derived from Clementine, and from this fit they found the relation that has been used to define the iron map of the moon. A similar process has been used for the titanium, and then in this way they produce these two maps you see here. Now we also have other data. So this is from Kaguya mission, and also this mission includes an instrument, the LISM instrument, which was composed by 3 subsystems: the terrain camera, the multiband imager, and the spectral profiler. And in this case, I will show you the map from the multi-filter camera, so the MI, which is an high spatial resolution multiband imaging camera. And in this case, we have 5 visible channels and 4 near-infrared channels. I indicated here the wavelength they have. They also have the spectrometer, but show what with the multi-imager camera, Lemelin and Alt produce the detailed global mineral maps from Kaguya multi-imager data. And you see here the distribution of olivine, the clinopyroxenes, low calcium pyroxenes, and plagioclase, which are the main phases present on the moon. They use this map between minus 15 and plus 15 degree in latitude, because the other region, so the high latitude region, has problem with the calibrations. And also the spatial resolution is very good, about 60 meters per pixel. In this case, they use a model to derive this data. And they, in particular, use more than 6,600 mixture of olivine, pyroxene, low calcium pyroxene, clinopyroxene, and plagioclase, so the main mineralogical phase present on the moon. And also the submicroscopic iron. Then they modeled the reflectance spectra from the multi-imager camera with those of the mixture, and they compare the modeled spectra with the assigned composition for each spectrum. And then they validated the model using the abundances obtained by the global elemental maps from Lunar Prospector. And in this way, they obtain this kind of maps from a multi-imager band. We have also another wide-angle camera on board the Lunar Reconnaissance Orbiter. In this case, we have 2 bands for the UV channel and 5 bands for the visible part of the spectrum. With this camera has been Sato et al. Obtained the distribution of the titanium with the LRO wide-angle camera. In particular, here this the distribution from the Maria using a method similar to those I showed you before for the Clementine map. At the end, just a few words regarding the Chandrayaan-1 mission and the Moon Mineralogy Mapper, which is a real hyperspectral spectrometer. And in this case, this is an imaging spectrometer. Cristian showed you before better what kind of data we have. So in the center, okay, you have just a picture of M cube, but in the center you see a typical image from M cube. So you have an image, and for each pixel you have the spectrum. in a number of band of 260 in the case you use all the range. In the table, I just put some information regarding the main characteristics of acquisition for the instrument. The instrument cover a range of wavelength between 400 and about 3,000 nanometer, and it tests two acquisition mode, the global and the target mode. So in the global mode, you have images at global coverage at 140 meters per pixel, while in target mode you have a better spatial resolution images, but just for some selected regions. On the left, I put some spectra from M-Cube data. On the top, there is just some reflectance spectra, while in the bottom, the same spectra after the continuum removal. The continuum removal is useful to visualize better the characteristics of the band, removing the spectral slope. So in this case, you can better see what is the position and the depth of the band with respect to the first plot. The main spectral parameters useful to map the mineralogy of a surface are mainly three, so the band centers, which give information on the phases present. In particular, here you have the band at 1 and 2 micron linked with the pyroxenes. Then the band depth, so the depth of a band is linked with the abundance of mineralogical phases, but can be influenced by grain size and also the presence of opaque material, which reduce the depth of a band. And then another parameter is the spectral slope, and this is indicative of theory maturity, but also composition and grain size effect. So in general, we have a steep spectral slope, so redder slope, in presence of mature terrains. So the terrains more affected by space weathering, but we can also have a compositional effect. For example, when we are in presence of volcanic origin material. Then when we have bluer slope, so shallower spectral slope, these are typical of unweathered material, so fresh material, but also we can have a bluer slope when, depending on the composition. For example, dark material is characterized by bluer slope, but also the ices. So in some way, these kind of parameters are useful to discriminate the mineralogy and the spectral properties of a surface. This is just an example of Apollo basin on the moon and the map of these parameters. So in the first in the top left image, we have just the reflectance in the visible. Then the distribution of the band centers at 1 and 2 microns. So you see, for example, that these smooth planes in the center and of the Apollo basin, and also on the bottom here, show higher values of these parameters, indicating the different composition with respect to the other areas outside. And then you also see the band depth distribution. So we have that the band depth are deeper in this area than in the rest of the basin. And also in the last one, we have the distribution of the spectral slope, which show that the region outside the smooth plane appear redder and then more mature than those of the smooth planes. So this is another way to derive the spectral characteristics of a surface. I finish here, and thanks for your attention.
Okay, so in about 20 minutes, we'll see this third and last part about compositional data, and we will focus on Mars surface mineralogy. So we actually know a lot about Mars surface mineralogy, thanks to lots of missions that during the last 20-25 years have orbited the planet and that had on board some kind of spectrometer. And in this presentation here, I will focus on mainly on the results of these 4 instruments, which 2 of them are thermal infrared spectrometer, and the other 2 are visible infrared spectrometer. So we have first we have the thermal emission imaging, thermal emission spectrometer, which was on board the NASA Mars Global Surveyor. That is the thermal infrared spectrometer, and it works on the wavelength range from 6 to 15 microns. Then some couple of years later, we have the thermal emission imaging system, which is again another thermal infrared spectrometer. And the wavelength range this time is between 6.7 to 14.8 microns. So these 2 instruments work as also the name says in the thermal infrared part. So they study the emittance of the surface of the planet. While these other 2 instruments here, the Omega instrument and the CRISM instrument, instead work in the visible infrared range, and they study the reflectance of the planet. So basically it's the light reflected from the surface. And they kind of have the same spectral range, but the spatial and spectral resolution is quite different, especially the spatial resolution. So CRISM spectrometer, as also you have seen yesterday, has a very high spatial resolution that can go up to 18 meters per pixel. And that allows us to study targeted areas on the surface. And it also has 544 spectral channels across both the visible and near infrared and infrared range. So it allows us to have a hyperspectral characterization of the mineralogy that we have on the surface. And you've also seen yesterday that it has 2 sensors. One is covers the visible and near infrared part of the spectrum, and the other one covers the infrared part of the spectrum. And these 2 ranges are joined in the most recent data, processes data from CRISM, the MTRDR data. And as also with other spectral instruments, you can also have mineral maps with CRISM. And in particular, you can have RGBs map, where you combine 3 different spectral parameters, and each color of the RGB is a different spectral parameter related to a certain absorption or related to a certain mineralogy. So for example, I'm showing you here the mafic RGBs that gives you information about mafic mineralogy. So in red, in the red channel, we have information about olivine. In the green, we have information about low calcium pyroxene. And in the blue, you have information about high calcium pyroxene. So these maps are very useful to assess the mineralogy of a certain area quite easily and quickly. So I won't talk much about these CRISM products, because you have a whole lecture basically about them from last year. So I warmly suggest you go to watch that. And if you are curious about how these CRISM products work, and if you want to know more information about CRISM in general. So we will instead focus on the results from CRISM, and also from the results combined with the TESS, TEMIS, and OMEGA previous observations. And so we will focus about the mineralogy of the planet. And all the data that we have gathered thanks to this instrument indicate that there is a very high, widespread, and diverse mineral assemblage on Mars. And here I put some of the currently identified minerals, and we have, for example, primary mafic minerals such as olivine, plagioclase, and pyroxene. And we also have lots of alteration minerals like phyllosilicates, like carbonates and sulfates. So we'll have a look in the detail at most of them. So starting with the primary mafic silicates, plagioclase and pyroxene are the most abundant minerals of Mars crust, and pyroxene can either be high calcium pyroxene and low calcium pyroxene. And here you can see basically a map from TESS showing you the distribution of these minerals. So you can see they cover, they are found almost everywhere on the surface of Mars, and in particular plagioclase and clinopyroxene are found mainly in the highlands of Mars, while the northern plains of Mars are mainly composed by plagioclase and volcanic glass. And here on the right you have the thermal emission spectrum of these two kind of surfaces. Olivine then is another important primary mineral that we have on Mars, and the composition of olivine ranges from iron-rich olivine to magnesium-rich olivine, and it's usually detected when we have materials, old materials that are exposed from depth. So, for example, by impacts. And also we have some olivine-rich lavas on Mars, as you can see, for example, on the bottom of this crater here. Moving on to another different kind of minerals, we have iron oxides, which are another mineral which is present almost everywhere on the surface of the planet, and it's mainly related to weathering of the crust of Mars. And it is the primary component of the soils and dust of Mars. So that's basically what gives Mars its red color here. And to also see the distribution of dust that we have on the surface of Mars, here I put a map from OMEGA showing the dust coverage on the surface of Mars, and basically the red areas are the one with a higher abundance of dust. And if you look at the surface at the visible wavelength, it's basically where you have the more reddish areas. So the brighter and red areas are the ones that on Mars are most covered by dust, while the darker areas are the ones where the dust coverage is less, and you have basically the mafic surface showing. So moving on to a different kind of minerals, we'll now focus on the aqueous minerals that we have on Mars, because these minerals are very important as they are indicative of a persistent water activity on the planet during the past. And we have lots of different minerals, meaning that the aqueous setting were absolutely different one from each other. So we have phyllosilicates, we have sulfates, we have carbonates, chlorides, other hydrated silica, and as you can see from this map, they're all widespread on the surface of the planet. Starting with phyllosilicates, phyllosilicates are by far the most abundant aqueous mineralogy that we find on Mars. And as you can see from the CRISM spectra here that I put on the right, there are also the most various, the most, they vary a lot. We can have chloride, serpentine, or magnesium smectite, iron smectite. We have lots of different minerals. And that's also because we have lots of different formation mechanisms for clays that can happen on Mars. Some of these formation mechanisms are surface alteration, like for example, pedogenesis, or other formation mechanisms are happen at the subsurface, like for example, diagenesis, hydrothermal alteration, or we can also have low-grade metamorphic. Clays on Mars are found basically in any setting, but in particular, they are found in fans and delta deposits inside craters. So it means that these craters were filled with water, that they were former crater lakes. They are also found in layered deposits, and usually in this case, we have both iron magnesium rich phyllosilicates and aluminum rich phyllosilicates. They are also found not associated to any fluvial morphologies, like for example, just in plains, in intercrater plains. And they are also excavated from depth. So they are found, we have phyllosilicate outcrops on crater walls, and we can find phyllosilicates on impact ejecta. Another important mineral, aqueous mineral on Mars, is carbonates. So carbonates are not that widespread as clays, as you can see again from this map here. They are basically concentrated here in the Nili Fosse area and the Tirrenia Terra, or at least these were the first carbonate detection of on Mars. Carbonates usually form in aqueous environment at neutral to alkaline condition, which are important condition if we want to consider the habitability of the planet, of the water. So actually we expect, so from this map here you see the carbonates are not that abundant. So this was a problem at first, because we expect that large-scale deposits of carbonates should form if Mars had a CO2-rich atmosphere in the past, which was thicker than the one that it has now, and if we had abundant water at the surface. So why don't we observe so many carbonates? So actually, there might be several reasons, some of which are more reasonable than others, and I put here some possible explanation. So it might be that Mars wasn't actually warm and wet, or wasn't warm and wet for long enough. It is also possible that maybe we had other greenhouse gases than CO2 on early Mars. It is also possible that some of the carbonate deposits are not observed because they were destroyed by subsequent acidic aqueous activity, because carbonates are not resistant to acidic waters. Or it might also be that actually it is hard to distinguish a carbonate signature in the spectra when it's mixed with other mineral phases. So we only observe carbonates in very carbonate-rich areas, but we might have carbonates in other areas, but it's difficult to detect them. So that was actually the case for some carbonates, because more recently, we have found some other carbonates spread around Mars. And these are usually found mixed with clays. So for example, we have carbonates occurrences at Oxyplanum, or in Valles Marineris area, or around the Hellas Basin. And so these carbonates are usually found mixed with aluminum-rich clays or with iron magnesium-rich clays, which in some cases makes a clear detection of carbonates challenging. So it took some time to develop more advanced way of studying CRISM spectra, or it took some time to have the it took some time to have the CRISM product that were more processed, so better to analyze. And so just in recent years, we start to observe carbonates also in other areas of Mars. Anyway, the one thing that it's very peculiar and unique of carbonates is that they are observed only in one case close to a fluvial lacustrine feature, and this is the case of J0 crater. So J0 crater, as you know, was chosen as the landing site for Perseverance rover. And one of the reasons why it was chosen is because here is the only known location of Mars where we have a clear carbonate detection and a fluviolacustrine feature, which is present. And that is very interesting to analyze. So moving on to the sulfates instead. Sulfates have a quite different settings in which they can form on Mars than clays, than phyllosilicates and carbonates. And they are also quite diverse, as you can see here from the prism spectrum of the sulfates that were observed on Mars. So usually the sulfates are formed through alteration of the crust, either in the surface or in the subsurface, through acidic groundwater or through acidic rain or frost. And they also form as from the evaporation of standing water bodies. So they form in environment which are not as water rich as carbonates and phyllosilicates. And the common sulfate occurrences around Mars are shown here. So we have lots of sulfates in the Valles Marineris area and in Meridiani Planum area and Arabia Terra. And you can see here on the right also a typical example of a sulfate-rich outcrop, which is usually very bright. So last slide, and to sum up what we have seen, especially about aqueous mineralogy, we have seen that having a different mineralogy means having a different environmental condition and chemical condition. For example, clays, phyllosilicates, carbonates form at water-rich condition with usually neutral alkaline pH, while sulfates, for example, form in a more acidic condition, and usually the water is scarcer. So finding carbonates, finding clays or sulfates can tell us a great deal of information about the environment in which they formed, and so about the geologic history of that specific areas of Mars. And they can also help understand how the climate and how the environment of Mars evolved through the epochs, because we mainly observe phyllosilicates around the Noachian era of Mars, while later we mainly observe sulfates. We don't have many phyllosilicates anymore. So that means that the environment started to dry up, started to become so increasingly water limited. And later in the history of Mars, we don't have sulfates anymore. We have oxides. So the environment also started to become increasingly oxidized. So knowing and studying the mineralogy is essential to assess these things, to study the history and evolution of Mars environment and climate. Okay, that was the last slide. Thank you for your attention. And if you want some references, I've listed them here. And you can also find the PowerPoint slides on Indico.